Function basics. A function is an input-output device that assigns to each argument in the domain to one and only one value in the range. There are a variety of ways to present a function. Here are 4 examples of functions. We can show a function with a map, a set of ordered pairs, a rule or a formula, or a graph. The vertical line test is used to determine if a graph represents a function. Place a ruler, or imagine a vertical line, parallel to the y-axis on the graph and move it from left to right. If the ruler hits the graph in one and only one point on the graph for all vertical lines that touch the graph, then the graph is a function. So if we take this ruler and move it left and right, we see that as we move it, here it only hits the graph in one point, here the ruler only hits the graph in one point, etc. So if you keep moving it back and forth, you see that it does pass the vertical line test. Since it only touches once, we can say that this relation passes the vertical line test and is therefore a function. Are either of these the graph of a function? Alright, so right here we see that this fails the vertical line test because this vertical line intersects the graph at 2 points. So even if we move this all the way over here, this does pass the vertical line test. However, if there's any point at which the graph fails the vertical line test, that means that it is not a function, even if there are portions of the graph that do pass the test. Over here, we see that it passes the test at every single point shown. So we can see right there, it only intersects once. As we move the vertical line over, everywhere we put it, it'll still only intersect once, so that is a graph of a function. As we saw on the previous slide, this is not a function, while this one is. There are numerous ways to represent a function, including set notation, a map, a graph, a table, and an equation that relates the input to the output. Function notation. For a function named f, the notation f of x is the value assigned to the input x. The letter f names a process, an input-output device, that assigns to each allowable input x an output or y value. Lowercase f is the device that maps input onto output. So here we have f of x, so we input x and we get f of x as our output. The device is set notation, a map, a graph, a table, or a formula. For a function named f, the notation f of x is the value assigned to the input x. The letter f names a process, an input-output device that assigns to each allowable input x an output or y value. Alright, so here's an example with set notation. Given f equals 1, 3, 2, 5, and 3, 7, evaluate f of 1. That means that when x is 1, what is y? So here we go through and we see, this is where x equals 1. When you put 1 into the function, you get 3 as an output. So this answer is 3. What about when x equals 2, f of 2? Here we find the ordered pair that has x equal 2, and the output is 5. Solve for x. F of x equals 7. When it's written this way, that means that the y value, whenever you see f of x, you can think that's the y value, equals 7. So we go through and we see that the y value equals 7 when x equals 3. Therefore, x equals 3. Here are the answers written nicely. The graph of a function. Suppose f is a function that maps a real number a, the input, onto real number b, the output. Then the point a, b is on the graph of f if and only if f of a equals b. There are finite functions where the elements of the domain can be counted, and infinite functions where the elements of the domain cannot be counted. Because of this, a set of ordered pairs, a map, or a table is a convenient way to display a finite function, while the graph of a function is a compelling way to display infinite functions. Here is a graph example. Given the graph of f, evaluate f of 2. Alright, so our input is going to be 2, our x value. So we go to x equals 2, and I'm going to draw a little vertical line. So this is where x equals 2, and we see that the point is right there at y equals -2. So the answer is -2. So when x equals 2, you just see where the red dot is, or where it intercepts the graph, and it intercepts right there at y equals -2. Solve for x. F of x equals 0. So that means that the y value is 0. Now that happens at 2 different points, which is okay. You're allowed to have 2 different points that end up at the same y value. You just can't have 2 separate points that have the same x value. So the answer to this would be when x equals 0 and when x equals 3. Both of those are going to give you a y value of 0. And we are correct. Evaluate. All right, A is f of 0. So when x equals 0, what is y? When x equals 0, so we look at this line here, we see the graph intersects right up here where y equals 5. B, f of 5 plus 3. So when x is 5, that's here, we see that y equals 0. So this becomes 0 plus 3 equals 3. F of x equals 0. So where does y equal 0? So y equals 0 here and here. This is where x is 1 and where x is 5. So x equals 1 and 5. Both of those give us a y value of 0. And finally, f of x plus 4 equals 0. Therefore, f of x equals -4. We'll subtract 4 from both sides. So where is the y value -4? 1, 2, 3, 4. So we look here and we see, y is -4 right where x equals 1, 2, 3. So x equals 3. And here are all of the answers. Here's a formula example. Given the function that maps an input x onto the output 3x plus 2, evaluate f of -2. All right, so all we have to do is plug -2 into the function. 3 times -2 plus 2. So wherever you see an x here, you replace that with -2. So 3 times -2 plus 2, that's -6 plus 2, which is -4. That's our answer to A. For B, solve f of x equals 3. All right, written like this means that this function equals 3. So 3x plus 2 equals 3. What is x? All right, so 3x equals 1, x equals 1/3. You can see that we have gotten both of these correct.